Welcome to Programming Rainbow. I'm just going to make a quick video. This is kind of an update of what I've been working on. So I have been working on creating a neural network in C to augment the game Don't Eat the Yellow Snow that we worked on before. And the code is on the GitHub page. So if you go to github.com, Programming Rainbow, and this one is called Yellow Snow Neural Network C. It is currently working. You can build it, and it's not finished, but you will need the basic C stuff. You'll need, for Arch Linux, you'll need base Devil, you'll need SDL2, SDL image, SDL mixer, SDL TTF, everything that you needed for the Snowman project. You can run it, but there's different switches, and I just give a basic overview of what's going on here, but let's just look at the code. So this is there's lots of different big words that everybody uses and fancy symbols that usually don't mean anything. A lot of times they're just making themselves feel good by using these large words. But this is a forward feed neural network, meaning the information flows one direction. It's also a multi-layered perceptron. It could be called that too. It's using very fancy terms internally, like Rectified Linear Unit for the activation functions on the internal layers, and on the final layer, it's using a Hard Sigmoid. And these words are a bit funny because when you see what they actually are, it's a load of nonsense. So let me just show you what the Rectified Linear Unit is right here. So it's this. This is the activation function. And all this is an if-else statement. This is just a ternary operator. So it could be the same as if output is bigger than 0. And then we could say in first out neuron. And we could say it equals output. And then on the else, we could just grab this, yank it, put it in, and it'll be 0. So it's just saying, what if the number is bigger than 0, we're going to have the number. If it's not bigger than 0, we're just going to have 0. So it's either 0 or a positive number. And that is a rectified linear unit activation function. And I'm just using a ternary operator here because I don't need this whole block of code. And then we get down to the hard sigmoid that I'm using on the output. I'm going to explain all this later, but I'm just showing you little bits of it just to kind of talk about what I've been up to. But let's get rid of that. So on the output layer, we're using a hard sigmoid. And all the hard sigmoid is true or false. If it's bigger than 0, it's true. If it's less than 0, it's false. Another ternary operator. So they use these big fancy words, and it's a load of nonsense. So this is just arrays, and we're just taking information, and we're taking the input, we're multiplying it by the weight, we're accumulating all the different inputs and weights for whatever the final layer or the previous layer was for a single neuron, and then we're adding a bias, which is just a number, an offset number, and then one of these activation functions. This, if it's bigger than 0, we're going to have the number. If it's less than 0, we're going to have 0. And on the final output layer, if it's bigger than 0, we're having true. If it's less than 0, we're having false. And I know there's more complicated networks out there. This is a very simple thing that I'm attempting to do here. I just wanted to understand how all the moving parts work. So this is the simplest version. This is not a large language model or anything like that. You do get these much more complicated sigmoid outputs, but I only need a simple Boolean output. So this is a hard sigmoid or a step function. Lots of big words that just mean it's a ternary operator. So yeah, so let's just see what's going on in here. And I'm not done with this yet, and I need more work on it. So the code is working, but I'm not happy with where it's at the moment. I'm still learning. So, but I just wanted to see all the moving parts of this. So let's just compile it. So I'm going to do a make clean, and then we can just make it. And if I just run this, say make run, it's just going to run it normally. And it should be, well, we'll see what happens here. We have, yeah. So this is normal play mode. So it's the way that the game would play. It has no AI functionality happening right now in the game. It just plays normal. It opens up an SDL window, and if I push space, I can control the character, and that's great. So that's the normal game. Now I could use make run, but also it created a binary that is over here called yellow snow. So I can run it, and I can give the switch AI on. I want to turn the AI on, and what's that going to do is it's going to load this file over here, this neural networks. This is my top, depends on how I set it up, but that file is my top 32 networks, I believe, and it's just going to take the very top network there, and it's going to use that, and it's going to populate, it's going to load that network, and it's actually going to use it, and it's going to allow the snowman to be controlled by the network. Now, the network's not very smart. Again, I'm still figuring out how to do all this, and I've only trained it up so much, but we'll see how it works. Okay, so I'm not controlling it now. It's the AI is controlling it. And it kind of looks like it knows what it's doing, but then it just runs into the yellow snow every once in a while. So it's not very great. It's not very smart. Again, I don't know if I'm setting this network up correctly, but you can see it's doing something. It is moving about, Okay. And let's see here. So the way I would train it now is I could give it different switches. So I could say AI on and then AI train, but if I do AI train, AI on automatically gets turned on. So I can do train. And if I do this, it's still going to open up a window, but it's going to run very fast. And yeah, it's going to go through one training section and then finish. So we're going to see what happens here. We'll see how long it takes to do one. So this is it playing itself, and it's actually running. I'm sorry about the sound. Let's see if I can. I have a. Oh, I didn't turn the sound off. Okay, it finished anyway. Great. Sorry about all that noise. So what it's done here is it's actually loaded up the top 32 networks, and then it's populated them out into 200 different spots. So basically, I have an array of. It takes the top 32 and it populates an array of 200 networks. And what it does is it takes each one of the original ones and it puts them in there. And then if it needs to populate a second one, it slightly mutates it. So it's going to put the original and a mutate. So there's probably one original and two mutated versions of each one of these 32 networks, whatever it takes to fill up the 200. And then it's actually running them just one time. And it's running this 200 networks one time. So it's playing 200 games. You just saw it play 200 games real quick, and that took 18 seconds. Now, we could be faster if I were to turn off the graphics, because we don't need to see anything happen here. Because that's basically one generation, but we only did one trial for each. We didn't run multiple trials on each one of the networks to find out how well it was. So let's try something else. So I have the AI. I want to train it. I'm going to turn off the graphics. Okay, now let's see how fast this goes. It's done. Now, that little pause there, it didn't even give me a time, did it? The little pause there in the beginning is a pause that I put in so I could read what was happening. I just wanted to see what's going on with my networks. You know, how it's set up. It actually understood my inputs. So I put a 1 second pause in there, and then it loads them up, and it didn't even tell me how fast it went. So let's train up a little bit more so we can get a time on this. So I'm going to leave the trials on 1, and let's do like 100. And let's not do this at all. So we're going to do one trial just like we've been doing, but instead of 1 generation, because that was too fast to kind of see, I'm going to tell it to do 100 generations. And I'm going to tell it to run each game 5 times. So it's going to take a network, and it's going to play that game 5 times, and it's going to take the score from each of the games. So whenever the yellow snow hits the snowman, the game ends. Whatever the score is gets accumulated for 5 times, and then it gets divided by 5. So we get the average of 5 games. And that's one of the networks. And then it goes to the next network. Now there's 200 networks. So it's going to play 5 games for each network, 200 networks. So that's going to be 1,000. And then it's going to do 100 generations. It's going to be 100,000 games running. It shouldn't take that long, though. But I'm going to put it on. Yeah, let's just do it. I should have thought about this. I didn't do the multi-threading. Yeah. I'm going to end it. Let's see if I can just do this. Okay. So we saw that that's not moving too quickly, right? Well, there's another thing I can do. When I compiled it, I just compiled like the debugging version. So I'm going to make clean, and then I'm going to do a make release that I allowed it to do some optimization. And we're going to see it's going to run a bit faster, just without giving it any other things. I'm going to tell it the same thing. We only saw it go to like 3 or 4 generations before I quit it before. We didn't allow it to finish because it was going to be too long and slow. I'm going to do the exact same command and see if it runs a little faster. Okay, we always have that 1 second pause, but you see this number is kind of rolling now. So that's pretty quick. So, each one of these is a generation, and we're running 5 versions of each one, 200 of them, each time this number ticks. And what we're looking at here, the output, is just outputs for me. This is the top 32, and this is actually not even the top ones. This is the bottom of it, because I can't scroll up enough to see the top. Right here, this is the top one, the next one. It puts them, I take all the 200 at the end, and I sort them, and then I take the top 32 of those, and I use those for the next generation to populate out again. So it finished, and it took 39 seconds. So that is, what did we say here? That is 100,000 games that it played in 39 seconds. So what if we did a little multi-threading? I'm a little bit afraid to do this while I'm streaming, but I'm going to say 8 threads. This is just a laptop, so we had 39 seconds. So I'm running the exact same thing again, but this with 8 threads, this should bring it down, roughly like 5 times or 6 times, something like that. That 1 second is always there, though. There we go, 11 seconds. Let's see if it can take. This is all the threads I have, so we'll see how the streaming works. Does it still stream okay? Okay, so it took 10 seconds, yeah. So it's about the same time. So this is how I would train it, except I wouldn't do 100 generations. I would do like, I've been doing like 10,000, 10,000, 50,000. I've been playing around with different things, and I've also changed. Right now it's actually going slower because I added more internal layers, or not more internal layers, but I increased the size of the internal layers. So that's a little bit about what I've been doing. I basically had to learn how to do multi-threading and input stuff. Let's close this off. So the way I'm getting the inputs, let's see here, is I'm just taking the arguments array and I'm just doing simple if statements on it with a stir compare. This is the first time I've been doing this kind of style. So, and I'm just, does it equal the actual, so nothing fancy is going on. This whole project, I didn't want to use any extra libraries. So if we look at the libraries that I'm using for this whole thing, this is what I'm using. And there's nothing fancy in here. There's pthreads for the multi-threading, but then it's just stdio, stdbool, stdlib, and time. This is the stuff that was already in here for the Snowman game. So I'm not using any. I'm not even using the math library. That's how simple this is. I'm not using the math library. Okay, so I'm taking the different inputs. When it comes to the threads, I check the next one to see if it is a number and if it's within a range for the threads. And then what I do is I change some of the different booleans, and I'm basically using a little config struct here to pass in to hold on to my different settings. And I was kind of outputting it right here just so I could see what's going on diagnostically. So I know what's going on. Basically, the multi-threading it's not turned on when if I have more than one thread rolling, the graphics is turned off because I run the game two different ways when the graphics is turned on or when it's turned off. When I need to do multi-threading, I run it a different way, just slightly different. The game still runs the same, but and let's show that off. So basically, all these files here on the left-hand side are the same for the Snowman. Let me just show you some things I would change in them. So for the player, I did make some minor changes, and what I've done here is I am passing in a new boolean for the graphics. So this is all the same, except right here. If my graphics is turned on, I do want to get the dimensions of the image I loaded. Okay. But if the graphics are turned off, I never actually load SDL at all. I don't load the SDL library, so I can't get the dimensions of the graphics. So that's why this isn't an if statement. If it is on, I'm going to get the graphics and I'm going to set up the key state. If it's not on, I hard coded the height and width. So I still have the height and width so the game can play, but I don't do any graphic stuff. And I think everything else is the same. Nothing else has changed in player. What does happen is I never call the draw function. This never gets called. So it's just subtle things like that. So the game is still the same. The add-ons to the game is the neural network right here. So this is my neural network. So this is what I have is I have inputs, and the Snowman game has 10 white flakes that you can collect, and then 5 yellow flakes. And each one of those has an X and a Y. And the Snowman itself has an X that can move back and forth. So my inputs are actually 31. That's 2 inputs for each flake and 1 input for the Snowman. So those are my inputs, and they're normalized. So I kind of just took the X and divided it by the width just to get it normalized. And I did the same for the height. So that actually means the snowflakes are negative numbers sometimes when they're above the screen. I was going to fix that, and then I just left it. I felt like it probably didn't affect anything. So my inputs here is 31. And then if we look at these, so this is what's going on here. I have an inputs array, which is just 31 doubles. All of these are doubles. Everything here is a double except the ints down here. So I have an input array, and then I have the first weights. I have a bias and an output. So basically, this is my hidden layer, and this is my second hidden layer. Both of these are the exact same. They do the exact same thing. They're the same size, but they need their own array. So for each node in the first hidden layer, I need an array of all the weights that correspond to the input layer. it's a two-dimensional array because I have, say, right now this array is size 30. It was size 15. So right now it's size 30. So if this is 31 on the inputs and this is 30, I have 30 here. And then for each one of these 30, I have 31 here that correspond to the inputs. So it's the weights for each one of those nodes. It has a whole array of weights for the inputs. And also we have a single bias for each node. So there's going to be 31 nodes here with 30 nodes here with 31 weights that correspond to here. And there's going to be 30 biases here. And then we're going to have the final output. So it's going to take whatever this node, say the top node, is going to take whatever the input number was. It's going to multiply it by its weight. And then it's going to go to the next input and multiply it by the next input's weight and the next input. And when it gets done with that whole thing, it's going to go to the bias and it's going to add the bias. So it's just multiplication over and over again for however many layers, for however many were in the layer before it, which is 31. We're going to have 31 multiplications for each node, and we have 30 nodes. But for the one node, we have 31 multiplications all added together, and then there is the bias added to it at the end. And then that's going to be the answer. And then there's an activation function, which is if it's above 0, it's the number. If it's below 0, it's 0. That's my non-linear, to break up it being linear, basically. And it just does that for every single thing. So that's how this whole thing works. This operates on this. The second layer operates on the output of that layer. This final layer operates on this layer. But with the final layer, our activation function is different. It is the hard sigmoid, which is the Boolean, the true or false. So that's how each one of my networks looks. This basically, there's 200 of these that I put into an array, and I save the top 32. And I use for the next one. And the fitness is just that number. However many white flakes that I got before the game ended, and then for 5 trials, and then divided by the 5 trials to get the average number, that's going to be the fitness number. And then I started keeping track of the generation because I wanted to know, is it really working? I wanted to know, is this thing really evolving? So I just chucked another int in here to just every time one of these networks gets mutated, the original will have the old generation number, but its mutation will have a +1 on its generation number. So every time one of these is mutated, it gets a number on it. Okay. So yeah, I'm just rambling on. There's nothing really specific. I just kind of want to talk about what I've been up to. But let's see. We have the update function, mutate function, and a rand function. So what happens is if this file exists here, it's going to pull it in and it's going to use the networks in that file. So we can continue on using already trained networks or continue to train the networks. But if this file doesn't exist at all, it falls back to just generating a random network. It just basically creates 200 of these and puts random numbers in them that are between -1 and 1 as a double. So if I rename this file or delete this file and then I run it again, it's like I'm starting from the beginning. It's just going to generate them for me. Okay, let's see. Did I change anything in this file? Oh yeah, okay, I just added those. So let's see here, the networks. So this is the fancy, here's the random, basically. It's just for loops through each of the things. It puts a random number on each one of the weights and each one of the biases. And that's all it does. The mutation is similar, except there is a probability. So I try to give it a 5% probability. So I go through all of the items again, but I'm running this 5% probability. So you see this rand function right here. is going to give me a number between 0 and 1. And this here is like my percentage of it being, so this is 0.05, which is going to be 5% if it's going between 0 and 1. So this is, so I've put this on all of them. So all of the weights and all of the biases get this whenever if that 5% is actually reached for this number generator, then it does the same thing. It mutates it, but instead of having it equal it, it just adds to it. So it could be adding a negative or adding a positive, however it works. So we're just using the same rand max to get us a number between 0 and 1. We multiply it by 2, and then we offset it to, so it can be between, instead of between 0 and 1, it's between -1 and 1. But the mutation rate is different. So it's actually not -1 to 1, it's -0.1 to 0.1 right now. But I've been playing with that. I'm not sure what to really do with it, so I've been messing around with the numbers here. But this whole thing is happening over and over again. This is just for loops where it's doing the simple thing that I said. Where the network update. This is the one that is the, what do you call it? The genetic algorithm that is going through and doing all these weights. So it's just taking, I'm just accumulating the output. I'm taking the input, whatever the input was, I'm multiplying it by the weight for that input. And I'm accumulating that up for all the inputs for that neuron, and then I'm just adding the bias. And then after I add the bias, there is the nonlinear rectified linear unit function on it, and that's done. And then the next layer, same deal. And then the last layer, it's the same thing again, except we have the step function at the end. And that's the entire thing. So it's running this network every tick of the game. Every time the game ticks over, every time the game updates, it updates where the flakes are on the screen, and then it asks what this neural network, it gets the input of where the snowman is, where the flakes are, everything else, and then it runs through this, and it gets an output, and then I feed that output into the movement of the snowman. So let's look at that. So the first thing I do, I pulled these out of the game loop. I used to have a bigger game loop down here, and I kind of pulled some stuff out to simplify it. So I pulled it out into a game update. So the first thing I do is update the flakes. Now, if the AI is turned on, so if the AI is not turned on, I update the flakes, and then I update the player. And I'm passing in two new booleans, and I'm just putting them as false. Okay, that's if AI is turned off. And then I check collisions and continue on with the game. But if AI is turned on, I run the neural network. So I've updated the flakes. I run the neural network. Oh yeah, okay. I'm sorry, I'm looking at this input right here. This input is the very top, the very first input, which is the X of the snowman. So this is getting the player. This is the player X position, and I'm dividing it by the window width so that I get a normalized value. Instead of 400, I'm going to get like 0.5. So I'm setting that as my input. And then I'm going through my flakes, and I'm doing the same thing for the X and the Y, all the way through all my flakes for the rest of the inputs. So now the neural network has all the inputs, and then I run that network update function that we just looked at, and then that's going to calculate what the output is. And then I'm going to run my player update, and the player update is going to take the outputs as these two. These two are just faults here. These are going to be booleans. So one is they move left and the other one's move right. But if AI wasn't turned on, I just put faults here. If AI is turned on, I'm getting the value out of the neural network. Okay. And actually, you can actually move it when the AI is turned on and the graphics are turned on. You can actually control it, and the AI can control it. So you can actually fight the AI how to move, because it looks for both of the movements. So you kind of see that there's different things happening here. So what else could we show? So I try to skip a lot of things. I had to make a secondary because of the multi-threading. I needed a function that is a void pointer, that returns a void pointer, and it needs also a void pointer as its input argument. So I didn't need all this stuff going on anyway in here because I don't need to update my game state. My inputs from SDL, because SDL is not even running, right? If let's see here. If I'm multi-threading, SDL is not even turned on. I don't even have a screen on or anything. So instead of running the normal game run, I run this game run multi. And this is what I need for the P threads. I need this right here. So since this comes in as a void pointer, I need to cast this void pointer back to the pointer to the game struct so I can use it as normal. But the only thing I'm doing is I'm hard coding the delta time. This number for the delta time gives me about what the movement that you would get if you were at 60 frames a second. But I don't want to be at 60 frames a second. I want it to run as fast as possible. So I just hard code the delta time. So I get fixed movement. I want it to have fixed movement, which is like, I think 5 pixels per game tick. The snowman yeah. I think it's 5 pixels. So the game can run as fast as it possibly can on whatever CPU, but you're still getting correct game timings. So I still have down here delta time being returned from the FPS update that keeps my game running at 60 frames a second or whatever I set it to, except when I turn AI training on. When I turn AI training on, that's why you saw the game running so fast. I don't do this at all because this has a game pausing in it to make the game run at a certain speed. Instead, I just hard code, 16.6 or 16.7, so I can get my movement that looks like movement that you would get at 60 frames a second, which is what my game was targeted for. Okay, so what else we got going on? So this is old. This is the original thing. We have the two new things is there's the network H, and you'll see there's nothing new added here. Like I really didn't add any. It's just pulling in main.h, and main.h doesn't really have anything new in it except p threads. And so we have the new AI one as well. I had to break this up into 2 modules because before the game.h and game.c controlled the game and everything was inside of the game. But since I need it to be multi-threaded, I actually need to control how the game is run. So instead of main instancing game, I have an AI layer that instance game, and it can instance many versions of game and run it over and over again. So that's what I've done here. I've made this AI struct, and it has a neural network. It has my top 32. One of these is a duplicate when I was changing things. It should have just one here, I believe. I'm holding onto the networks part of it, just the top one. And the game itself holds onto its section of the networks that it needs to run. So when I do multi-threading, I need to delegate out, hey, you run so many versions of the game, the next thread runs so many versions of the game. So the game itself holds an array of networks, but the top 32 is held in the AI thing. So this right here is not a pointer to a game object. This is a heap allocated array of games is what this is. And so are these. These are heap allocated arrays. I know it looks like a pointer to a neural network. It's actually a heap allocated array of neural networks, and so is the game. Because if I'm multi-threading it, I need 16 versions of the game, instanced. So, and we can see that. So I just have this AI config that I pass in that just has the booleans and the simple numbers, whatever I need set up. But here I'm just calicking the amount of neural networks I need, the top ones, and then I'm calicking how many games I need, and this is based on how many threads I want. This is a bit complicated. Not the loading of the network. That's actually not too bad. So the way I store the network is just literally in bytecode. It's not human readable. It's just simple. It's just I'm storing the array directly as bytes. So if I open this file, it looks like nothing, But it's the simplest thing to do, and it works. So it does exactly what I need it to do. So I don't really mind. I don't need it to be fancy. Come on, there we go. So I just load it very simply, and then when I save it, where is the saving? If I can't load it, if it can't load, I tell it to right here. Wait. Yeah, I tell it to basically create a random. Right here is if it couldn't load the file, it falls back to just creating a new random set of networks. The population thing, I'm going to have to work on this. The population of the networks is a bit complicated because I have to divide up what's happening. So if I have 200 networks that I want run, and say I'm running 2 threads, I want to put 100 networks on one thread and 100 networks on the other thread. I want to get the answer, and I want the top 32 of those 2 threads when they're done. So I want to hold that top 32 again, and then I want to remutate that top 32 back out to those 100 in each game again. So this one is something I was scratching my head about for a long time. It's probably not the best way to do it, but I was just thinking about how to do that. Yeah. And the thing is I also, if I have the, say if I have 32, that means I'm taking 16. Then my top 32, I need to take 16 for each thread. And then I need to take that 16 and I need to populate it to 100. So I need to add the original 16 in, and then I need to mutate the rest. So that becomes a bit complicated here. So this part here is a bit annoying to figure out how to make it work. This one is just saving the servers back to the file now. And like I said, it's not fancy. I'm just taking the array of networks and writing them directly to a file. So it's just a bit, bit coded file. It's not any kind of JSON or any of that nonsense. I'm not doing any of that. This one just goes through the however many games I have, and it just finds the top 32. And this is a very dumb, I wasn't trying to be fancy here. If it finds the new network got a bigger number, it just moves all the other networks down. It goes to the very last network, or second to the last, and it moves it to the last, and the one before that moves it to the second to the last, and it just goes all the way back. And it's just a very simple thing. So it could be optimized, but I don't need it to be optimized. I just want it to work. And here's how I'm running it. So I'm thinking about whether it's going to be single, so I have to set up the P threads no matter what. I can't put it in an if statement or the compile or complain. But if I have graphics on, I run the normal game. If I don't have graphics on, I'm going to create as many threads per how many variants of the game I want to run. And then I'm going to join them together. So I'm just creating the threads and then I'm joining them back together. After I join them back together, I'm going to go get the top 32 again, and then I'm going to put them back out to those I'm going to populate them back out again afterwards for the next generation, and then it's just going to go in a loop for however many generations I have. So yeah, so the pthread part is just here. So I'm just making threads and then joining them back together. So the complicated part was just how do I get the networks divided up in such a way that the games can work on something for enough time where it's worthwhile to have multiple threads. Yeah. And I only save the game if training is turned on and the graphics is turned off. Because I noticed sometimes when the graphics is turned on, I would tell it to close a game or skip a game, and then it would leave one of the networks empty. So I was just like, yeah, if I'm just looking at it, I'm not actually training the network if I'm looking at it graphically, so I'm not going to save those networks at that time. So yeah, so I'm still learning about this. So if anybody knows about this stuff and they want to check out my code and give me some suggestions or some fixes, or I'm still trying to figure out how to properly train this. So right now I have let's go in main H. So right here is kind of, this is like my little AI config that this is my little AI config that I can send into the different places I need it to. It goes into game and it goes into the AI. I don't think it goes anywhere else. Parts of it do. But right now, I've set a lot of these to 1 because they're defaults. They get, you can turn them on through the command line switches. But I'm hard-coded right now. I'm 200 and I'm at 32 for the top variants. So basically, whatever the top 32 is, those original 32 get put back into the 200, but also mutations of those top 32 get put back in as well. And let's see. Oh, the hidden layers were 15. So what's on GitHub right now is 15. So I was just playing with it before making this video. I set it to 30. I don't know what's the best solution for this type of game. Like, again, if anybody does know, if you could help out with any great information. I know the mechanics of this is not too difficult, but I've never made this type of thing before. So it's like I'm just kind of groping around in the darkness, not really knowing what I'm doing here. So I can get the code to work, but I don't know if I'm doing it the best way. So I've messed around with different things. So my probability is at 5%, and this is my mutation rate, which is when something does get mutated, it's going to be whatever the number is. So it's going to be a number from 0 to 1, but then it's going to be multiplied by 2 and should be shifted. I have to double check that. It's so it should be between -1 and 1. And then it's going to be multiplied by this 0.1. So it's going to be between -0.1 and 0.1. I did have it before at 0.5, and I did have it at 1 before. And I'm not actually sure what is the best route, or if there's a best route. So again, if anybody knows about that, they could super help out with that. This is just my inputs. There's, like I said, 31 because I have 1 snowman and 15 flakes. And the outputs are 2. I'm actually not telling the neural network what color the flakes are. So I'm hoping that the neural network understands that the bottom 5 flakes are yellow. They're the bad flakes, and the top 10 are good. I'm assuming that can be trained into the network. I'm not 100% sure, but it does appear to be that way when I play it. It does seem to understand what's happening. But anyway, that's a very long-winded way of saying what I've been working on. I kind of find this interesting because everybody uses these large words and everything else, and they got these. And if you watch other videos, when they talk about making it from scratch, they start using libraries. They start writing Greek letters on the screen, and it's a load of nonsense. They're just arrays. You're just mutating one array to the next array. You're just multiplying, accumulating, adding an offset, and then breaking up the whether it's linear, doing some kind of activation function. And I know it's nice to have all these Greek letters and to show off, but I just wanted to see how it works. And I didn't want to use any libraries. I just want to see what's a way to make this happen. So anyway, yeah, if anybody, like I said, wants to share, wants to check out the code, they can check out the code. When I do figure it out and I'm happy with it, I'll break it down into videos that explain it way better in steps. But right now I'm still playing around with it, Okay. So yeah, if anybody has any questions or whatever, they can ask. They can play around. And these networks are already partially trained, different amounts. And you don't need them. You could just rename one of them. If there's no network there, it will automatically create a new untrained network with random numbers in it. It shouldn't have zeros in it. It should be random numbers. And then you can obviously put it on the multi-threading, use the compile it with the release, put it on multi-threading, and you can start training it up. And I was working on this for so long before I figured out how to put the multi-threading on it and how to really optimize it for speed. I just did it in the last day or two. I started getting it really moving fast. And it can do, I think I trained up like 100 million. I trained on 100 million games earlier today in like an hour or two or something. Some crazy number. But I wasn't getting the results at the end that I hoped to see. So I'm sure I'm doing a lot of things wrong here, but hopefully I'll figure it out or somebody can let me know. Okay, so that's what I've been working on, and it's getting there. It's like it's fully functional and all that, but it just might not be done the best. Okay, so like I said, it is on GitHub here. It is going to change. It's not in a ready state, but it's totally compiled. It compiles. It shouldn't error or anything like that. That was just what I've been working on since I did the last videos. So I've been kind of working on this nonstop and just staring at the screen sometimes, a little bit lost, trying to think about how can I separate this out into all the different, how could I divide this up into different kind of workloads that can be worked on. Okay, so I hope that was fun to watch. That is way too long of a video just to cover what I've been covering. But anyway, I hope you enjoyed that. And if you have information or if you think this is a cool subject, you can ask questions or whatever. I hope I can explain. But if you have better information than I have, please share that so we can all kind of know what's going on, so we can kind of understand these simple neural networks, the basic ones. So we could put some fun things in games. We can make different type of games that maybe you have an AI enemy that, instead of just programming it walk left or walk right or do this one thing, it could actually have some interesting personality to it or something. So this is, it is interesting. Yeah. So I think that's going to be it. I hope that was entertaining, and have a good day. Bye.